Let me see if I can put in full screen. Ah, good. Are you seeing my screen?
Yes, sir. Yes, yes, it is visible, sir. This is visible, Professor. Hello,
Okay. Is it okay?
Yes, this is okay. Yes, sir.
Ah, good.
This is today the lecture will be given by Professor Neto from Sao Paulo University, Brazil, and the topic of this lecture is nonlinear optical technique, the Z scale, and low density proteins. I think it is very interesting topic for the common people. Even the who don't have interest in they don't have physical background, but it seems to be a biological topic. So I request Professor Neto to start his presentation. So Professor Neto, over to you.
Okay. Well, first of all, I would like to thank Anup for this very kind invitation to give this talk, for this interesting meeting that you have in India. We are a little bit far from you, but with the Zoom and these technological tools, we are able to discuss with people and friends for all over the world. So many thanks, Anup, for the kind invitation. Well, my lecture today will be about some nonlinear optical properties of the low density lipoproteins that we find. We can find this in our blood, and you will see that new techniques from the condensed matter physics can be used for a very interesting subject, that is to identify the modified LDL particles from the native or good LDL particles. This work started in my lab about 15 years ago, and I will make a brief review of what we found, and I hope it will be interesting for you. So this work was mainly performed at the University of São Paulo, the Institute of Physics in São Paulo, Brazil, where we have this type of technique, and it's a very performant setups that I will show you in a while. This is a bench of collaborators from different countries, postdoc people which came to Brazil, and is essentially a multidisciplinary work. So we have physicists working with physicians, with immunologists, with also odontologists, dentists, as you will see, chemists, and mathematicians. So all these people are from different parts of Brazil, and some of them are from different parts of the world, which make some theses and postdocs in my lab in São Paulo. Well, when we speak in nonlinear optics, it started essentially in 1960 when Meinman essentially not discovered, but realized the production of the first monochromatic collimated coherent light is the laser beam. And what we name nonlinear optics is basically the interaction of the radiation, the light, with matter. But it's important that to put in evidence the nonlinear phenomena, it's important to have high electric fields in the electromagnetic wave radiation and high intensities. So I give you here some information, some numbers about what is this strength of the electric field is of the order of 1 kilovolts per centimeter, and the intensity is about 2-3 kilowatts per square centimeter. So it's a high energy concentrated in a very small piece of space to put in evidence the nonlinear optics. So we will see that it's possible to have not only information about the nonlinear optical absorption, different types of absorptions, and also the nonlinear index of refraction due to the interaction of this high electric field with matter. Well, and when we speak in nonlinear optics, in condensed matter physics, fluids or solids or even gas, it doesn't matter, we can think that we have a problem which is basically named as self-focusing of a particular Gaussian laser beam or self-defocusing. So let us see with the hands what is going on when we shine a sample. Imagine this is a sample, and this is a profile of the Gaussian beam that you see here. This is the intensity of the laser beam, a Gaussian profile, so it's more intense in the center of the beam, less intense in the borders, and you have a cylindrical symmetry along this axis. Well, so this is the profile of this beam, which will interact with a material. Could be the LDL particles, could be, for example, a thin film or ferrofluid that we will see tomorrow in another lecture. But imagine that you have plane waves interacting with this medium. If this medium has no nonlinear optical response, you have this plane wave reaching the sample, it will pass through the sample, maintaining or keeping the plane wave shape of the beam. On the other hand, if you have a medium here, which has nonlinear optical properties, what you see is that when this beam will cross the sample, the velocity of the wave near the borders with respect to the center of the beam could be different and could be lower or higher, as you see here. So in this case, this material looks like a convergent lens that is placed in front of the beam. So you have some self-focusing process. It means that the medium will interact with the laser beam here, with the radiation. It will change the property of the medium, and the medium will change the property of the plane wave, which will be like a convergent beam after passing through the sample. So this is the so-called self-focusing effect. But as I told you before, there is also a self-defocusing effect. If your material has now the property that in the hotter part of the sample, the hotter part of the beam, the velocity of light increases with respect to the colder part of the beam, you have some type of divergent lens here. So you have a defocusing effect, and in condensed matter physics, you have both types of materials. you have materials which will act like a convergent lens, and we have also materials which will behave like a divergent lens. So this is basically the physics of the nonlinear optical response of a medium when it interacts with a high intensity electric field, in this case. Well, in our case, we will see one particular type of response, which is named the thermal lens. So the convergent or divergent lens that will be formed by the interaction of the radiation with the medium will be named here the thermal lens. Why? Because the sample will be heated by this Gaussian type beam, which has a non-uniform spatial distribution of intensities. So in this case, it's basically a non-local process because you have the transmission of heat, the propagation of heat from the center of the beam of the sample towards the boards of the sample. And this particular physics will change the refractive index of the medium. So these are basically the equations of the modification of the heat. So this is basically the heat which changes with time, which is proportional to the intensity and the heat conductivity of your sample. This is basically the R is the distance from the center to the border of the beam. And after that, you have a modification of the temperature of the sample as a function of time and a function of the position from the center of the beam towards the end of the beam. This is essentially due to the thermal diffusion coefficient. So big T here is the temperature, this is time, the thermal diffusion coefficient. Here, rho is the CP, specific heat of the sample, rho is the density of the sample. So this particular number here, which is the thermal diffusivity of the thermal constant of the medium, will be essentially due to this ratio between the conductivity, the specific heat, and the density, mass density of the sample. So you have a profile of the temperature, which is a function of the temperature and the position. Remember that R is the position counted from the center of the beam towards the border of the beam. So this will change as a function of time here and as a function of the distance from the center of the beam. Well, so if we are able to measure this with a particular temperature, with a particular setup, we are able to determine this parameter from the particular medium you are interested in. So as you will see at the end of the talk, this number here could be a new parameter, which will be necessary for the physicians, for example, to determine if the guy with a blood exam with a particular number of DTH is necessary to take statins or not. So this probably could be in the future a new parameter that the physicians will ask you to measure in your blood exam, routine blood exam. Well, so as I told you before, there will be a change in the index of refraction of the medium, and this modification of the index of refraction has basically three different sources. The first one is the modification of the temperature as a function of time and position. And this parameter here is the thermal optical coefficient. So this is one source of non-linearity in materials shining with a high intensity laser beam. There is another source of nonlinearity that we will not treat in this talk today, which is named the matter lens, which is essentially due to a modification of the number of particles in the center of the beam due to the Xray effect. The Xray effect is a very interesting effect which was discovered for more than 100 years ago. When you have two plates, for example, one hot and another cold, and you have a colloid in between them, you will have, by this difference in temperature, the different concentration of particles of this colloid near the hot plate, different from near the cold plate. So this is named the Xray effect. And when this occurs, you have basically the modification of the index of refraction of your sample, of your material, due to this matter lens, which is essentially the Xray effect. And the third one, sorry, I'm not so used with this. Okay, and the third one is what we name now the electronic lens that we will see tomorrow in the second lecture regarding the nonlinear optical properties of matters. What happens here? What happens is that you have electrons in a particular level of your electronic gaps, and when the light is incident to one electron here, it will be promoted to a second one. And when the case, you have a modification of the index or refraction of the medium due to this electronic interaction with light. So these two effects here, which are also nonlinear, we will not treat in our discussion today. We will treat just the first one, which is basically the thermal lens. Well, so as I told you, it's possible to substitute our sample by a lens. You can ask ourselves, what is the focal distance of this lens? So the focal distance of this lens is related to the thermal optical coefficient, the modification of the temperature with respect to the distance from the center of the beam. And here you have essentially the sample thickness. So if you are able to measure dN over dt, and you have the difference of temperature from the center of the beam to the border of the beam in your sample, we are able to measure the nonlinear index of refraction. This part here is the linear index of refraction, which we are used to measure, for example, in the university, when we have students to measure the index of refraction of some material, we basically measure this part, which is the linear contribution to the nonlinear index of refraction. So what we will measure today, and we will see what is important in the case of the LDL solutions, is the thermal optical coefficient, is the nonlinear contribution to the index of refraction. Well, so the thermal lens, if we use this technique that we will discuss in details in a while, that's named the Zscan setup or the Zscan technique. If you measure the intensity of the beam in a particular position and you compare when the Z is very far from the focus, I will show you this in detail in a while. Just these equations are the equations that we will use to fit the model to the experimental data. So don't take too much attention to these equations now. But the important point is that if we measure the normalized transmittant of light passing through the sample, we normalize this with respect to where the sample is very far from the focus of the laser beam. You see the introduction here of the focal length distance. All the other parameters are known. So the only thing that you don't know is the focus distance of the lens formed during the nonlinear optical interaction. And when we put here this Ft, the unique parameter that we don't know, so is a fitting one parameter only. And we will see that the thermal diffusivity or the thermal diffusion, the thermal coefficient will be proportional to this parameter theta that I will show you in a while. What does it mean? So if we are able to measure this with a technique that I will show you in a while, we are able to have the thermal diffusion of the sample, you are able to have the focal distance, you are able to have the nonlinear response to the medium, which is dn over dt. Well, if some of you are interested in more details about this, we published the papers many years ago in the Journal of the Optical Society of America B, where we see in details which are the difference in the index of refraction when the material interacts with a very high intensity laser beam. You will see the modification due to the temperature is the thermal lens, the change in the volume fraction of the particles in a colloid is the Xray effect, and the electronic process, which is the electronic lens that are formed. So if you are interested, you can see in this paper, we have all of this in details. And what is interesting is that each of these phenomena, they have a particular time scale. So if you are thinking about thermal diffusion, the thermal diffusion occurs in time scales of about milliseconds. If you are interested in the change in the volume fraction of particles in a colloid, the time scale involved here is about 1 or 2 seconds, so orders of magnitude different. And if you are interested in electronic process, the time is still smaller, is of the order of femtoseconds, 10 to the minus 15. In the lecture of tomorrow, we will discuss a little bit about this lens, the matter lens, which is formed in the Xray process, and mainly the electronic process in the case of magnetic materials. So the optical path length, this is the sample thickness, this is the linear index of refraction, this is the contribution due to the thermal lens, this is the contribution due to the Xray lens, and this is the contribution from the electronic lens. So depending on the setup you have, the time scale of the experiment you are doing, you can prove different physics of your material. Well, so the motivation to study LDL here is very interesting because I am a physicist of condensed matter physics. I'm not a physician, but there is a very important problem that everybody faces, which are the cholesterol. The cholesterol is this molecule here, which has the property of being non-soluble in polar solvents, like water and like blood. But cholesterol is essential for life. Without cholesterol, you cannot reproduce new cellular membranes. You cannot do the cellular membranes if you don't have cholesterol. So it's important to have the cholesterol in the different parts of the body. Well, how can we do that? Well, the evolution of the man make this two types of carriers of cholesterol from the liver, which is the most important producer of cholesterol in the body. And these main carriers are basically the low density lipoprotein, which makes the direct carrier, is the direct carrier of cholesterol from the liver to the different parts of the body, and the high density lipoproteins, which is basically the one which makes the reverse, is the reverse carrier of cholesterol. So if you have excess the cholesterol in different parts of your body, the HDL particle will take this cholesterol and will leave this to the liver and will be excreted. So essentially, we had the problem, which was how to take this particle or this molecule, which is non-soluble in polar liquids, and we have to take this from the liver and put, for example, near your head. So how to do that? So the evolution of the human being made this type of what I call the nanosubmarine, okay? And the cholesterol is essentially inside this nanosubmarine. Let's go here again. Okay, so this nanosubmarine will involve the cholesterol molecules on it and will deliver to the different parts of the body. Well, this is the sketch of a HDL particle and is usually named the good cholesterol. And this is the LDL particles, which is usually considered the bad cholesterol. But it's important to remark that there is no good and bad cholesterol. Cholesterol is essential for us. If we don't have cholesterol, we are dead. So this particle makes the is the direct carrier of cholesterol from the liver to the different parts of the body. If everything is okay, the HDL will take the excess of cholesterol and will remove from our body. So if these particles are okay, they're not modified, everything is going on, no problem, and we have health. Well, this is the electron microscopy just for you to have an idea of dimension. These are the LDL particles. The typical diameter of the particles is about 20 nanometers. You see the HDL here, much smaller, more dense, because it's named the high dense lipoprotein. This is low dense lipoprotein. And you see that they are almost spherical shape, okay? And you may ask why someone devoted for more than 20, 30 years working in liquid crystals are interested in LDL particles. The response is here in this sketches. I worked with many years in lyotropic liquid crystals. So lyotropic liquid crystals, you have amphiphilic molecules. These are the head of the molecules. This is the carbonic chain of this molecule, this amphiphilic molecule. In water, you form this type of structure, which is named micelle. But if you see the LDL, essentially you have these green parts here are the heads of the amphiphilic molecules, the phospholipids. These are the paraffinic chains. And inside here, you have the triglycerides and cholesterol. You have some cholesterol here also to make the stability of this not a cellular membrane, but the membrane of the particle. So you see that the cholesterol is essential to maintain or to keep the stability of this structure. Because of this, in our cells, you have the cholesterol and they are essential to be present to stabilize this type of structure. So you see that the dimensions are not so different. And the type of physics that we do here in lyotropic liquid crystal may be translated to this, may be moved to this without so many effort in the first thought. But after that, you will see that you need a lot of information from the medical schools, from the immunologists, to have an understanding of these particles and how it works in our body. Well, this is what we call the trip of a good LDL particle. So you have here your nanosubmarine. This is the LDL particle, and this represents a cell membrane. And here you have the receptors for the LDL. Well, when the particle reaches one of this, the particles reach one of these receptors, if the receptor recognizes the LDL, it's okay. It will be internalized in the cell. It will break. The cholesterol is delivered. You have the formation of different substances here. More of these receptors are formed. They go outside, and the excess of cholesterol will be taken by the HDL particle, which will go out of the cell, and everything is okay. Well, the problem arrives when these receptors did not recognize the LDL particle are as something good or proper of the body. For example, if you have a virus, if you have a bacteria reaching this type of receptors, it will not be recognized, and the immunological system of the body will fight against this modified LDL particles. And this is essentially the process of formation of plaques in the arteries of the body, in the heart, in the arteries here. So the formation of the plaques is essentially a fight of our immunological system against modified LDL particles. Okay? So it is important for us to differentiate, to have a particular technique that will differentiate the good LDL particles, which are recognized by the receptor, from the bad LDL particles, which will not be recognized by the immunological system and will be essentially, we will try to remove this from the body, and this process will lead to the formation of the plaques. So this is the motivation of our study. Here you see a more concentrated sample of normal state of the LDL. And if you have modified LDL, you see here that they have a different shape, okay? They're more aggregated, like corn, for example, in this picture here, electron microscopy. So you see that the modified LDL has a shape very different from this one, and the properties of this material, in particular the nonlinear property, could be something different. And if we're able to put in evidence these modifications of this changes, we can identify the good LDL from one side from the bad LDL of the other side. So this particular state, the modified or disease state, makes the formation of aggregates, nucleation unities, fractals, vesicles, and this is essentially the plaque that we start to have in our body since we are born. So this is a process that occurs in our body since we are born. Well, more images. Here is the normal LDL, and we see that we can mimic the modification of the LDL in the body. For example, for in vitro studies, we can oxidize the LDL introducing copper sulfate in the LDL solutions. When I speak LDL solutions, is essentially the LDL particles in water, okay? Here is with iron. You see the modification due to iron is much more impressive than the modification here with copper. And you can see also some bridges, which you have between LDL. This is the pre-formation of the aggregates or the fusion of LDL. At this point, you have not fusion, you have essentially a bridge between two LDL particles. And after that, you can have a mass, which is basically the plaque forming in the body. So our idea here is, okay, let's see if the nonlinear optical response of native and modified LDL are different. If they are different, we have a fingerprint of this LDL. Good LDL with a particular fingerprint and good LDL with a particular fingerprint also. How to put this in evidence? Well, one thing that we knew is that in the body, if you have hyperglycemia, hypercholesterolemia, periodontite, which is an illness that you have in your gums, gingivitis, are pathogenic factors mainly in patients with diabetes. Also, high levels of cholesterol and the increase of concentration of modified LDL generated by this oxidation and glycation. So these are facts that we know. And what we will do now is try to put in evidence using the nonlinear optical properties. Well, so the main goal today here is to study, the effect of the glucose in periodontite and gingivite in the structure, nonlinear, and linear optical properties of these LDL particles. Obviously, the structure and linear properties, I will pass very fast, and I will focus our attention to the nonlinear optical properties. And the techniques which will put this in evidence are the Zscan for the nonlinear optical properties, small angle X-ray scattering for the structure, DLS, my God, DLS for the dynamic light scattering, UV spectroscopy also for light in the linear optical process. Well, let us make an experiment together. What is the Zscan technique? The Zscan technique needs basically a laser beam here, okay? This is a chopper. A chopper is basically a disc with some holes in the periphery of this disc. And we'll turn the disc with respect to the center of it. So when the hole is there, you can pass the laser beam through here. If the hole is not there, the beam will be stopped. And this chopper gives essentially beams or beam, the time scale of this beam, as you see here in the detector, in this detector, which I will name the detector red. This is oscilloscope, okay? This is the beam splitter. So part of the beam will come to this detector you are seeing here. So no beam here, beam during about 30 milliseconds, no beam, and you make this as a function of time. This shutter is not important. You can forget this for a while. So this is the Gaussian profile of the beam, hot in the center of the beam, and colder, more cold, like let's say like that, in the borders of the beam. So what we will put now is a lens here, a lens of glass. We have the focus point at that position. After you have the focus process here due to this lens only. You have a detector here, which I'll name the detector blue, okay? And in front of this detector, we have an iris, a small hole, just a small hole. So if you don't put the sample at that region here, you have the red detector detecting here during the 30 milliseconds, and the other one will detect the blue detector here, will detect the beam also, a square top hat beam with 30 milliseconds. So this is a chariot where we will put our sample, okay? So imagine that the sample now, oh, sorry. Okay, so let's put the sample far from the focus. Well, obviously, the power of the beam is the same. The power, the energy per time is the same along all the Z direction. This is named the Z direction. And we will scan the sample along this direction. Because of this, the technique is named the Z-scan. So the horizontal axis is the Z-axis. And if we are far from the focus, the intensity, which is energy per second per square centimeter, is not so high. So you have the response here at this iris in the blue detector, essentially the same thing. But if you approach the focus of the laser beam, where the intensity is higher, you will start to see an increase of the energy as a function of time after you have the stabilization of this and after the case when the laser beam is turned off. If you go further, you go to the other side, you see that now the lens, which were convergent in the left side of the focus, is now divergent. So you see that the intensity here is lower as a function of time and stabilizes, and after it will be the same when you go far from the focus. So the measurement in the Zscan technique is essentially this. You take the sample from the left to the right, you stop at different Z points, and you measure the intensity as a function of time. You normalize this transmittance, and this will give you essentially the information about the physical process which is taking place in your sample. Tomorrow, we will see that the laser beam we will use to see electronic process could not be shopped by a shopper, because you cannot have femtoseconds with a shopper. It's not mechanically possible. So we will use a laser which is already a femtosecond laser. So this will be described to you tomorrow. Well, so what we measure basically is the transmittance, the normalized transmittance, so the intensity at the blue detector as a function of Z, as a function of time, with respect to the intensity when we are very far from the focus point. Okay, so the normalized transmittance we have, we can measure this. We can also relation this to the focal length of the thermal process, which is defined here in this CT. If you see the publication I give you around 2003, you will see these different types of thermal, Sorel, and electronic lens defined by these parameters: C thermal, C electronic, C Sorel, which is basically dependent on some geometrical parameters of your wavelength of your laser. All of this are geometrical parameters. And what you have essentially is one fitting parameter procedure. So the CT, which is present here, you can compare with your measurement, and you have dn over dt. So all this parameter, which is a dimensionless parameter, is named theta. And I'll give you now a typical Zscan result, where here you have the normalized transmittance as a function of the Z position here of the sample. And you see, this is a typical response of a nonlinear optical sample, which you can have interacting with high electric field. So just to give you a flavor, what we will discuss in a while. This is the response here of a strongly modified LDL particle. So if you, for example, make a copper or iron in vitro modification of LDL particles, this peak to valley distance is 0. So this is the fingerprint of the modified LDL particle. This, with triangles here, is the response of the native, the good LDL particles. So you have a different response, a different fingerprint of a good LDL particles, so with higher value of theta, and strongly modified LDL particles with theta almost to 0. So this difference between good LDL particles with big peak to valley distance and highly modified, almost nothing, will give us the fingerprint of the bad and the good LDLs. So what we did, the first part of the experiment I am telling you today, we made the glycation in vitro, essentially to mimic diabetes. So you take LDL particles from a healthy person, and we modify this LDL with this process named glycation. We are basically simulating the diabetes in the people, okay? We are simulating this diabetes, making this glycation in vitro in different degrees. So this is what we will see now. And as I told you how we do that, we take the blood for what we call normolipidemic donors, okay, take from healthy people, and we separate this LDL from the other particles by serial ultracentrifugations, 10 to the 5th G, at 4 degrees centigrades. So we let for a while there, almost 2 days in the ultracentrifugation process, and we will separate the very low lipodensity, very low lipodensity protein here for the LDL, low density lipoprotein, from the high density lipoprotein. You take the pipette, you remove what you want, and we make this analysis in vitro or in vivo, depending what we are doing. I'll show you in a while, that we are able to take these good LDL particles and modify this by simulating the diabetes in the people. Obviously, we take this from volunteers. When you don't have volunteers, we take our students. So you are invited to give blood to us to make our studies. We are very happy to that. Well, so the in vitro glycation, like glycation, which mimic the diabetic people, is essentially, there is a procedure which was determined by the physicians and immunologists with this glycolaldehyde that we put in particular temperature during days. And after that, we have for each day, 1 day, for example, 2 days, 3, 4, 5, until 6 days, and you are modified progressively the LDL particles due to glycation. So you simulate what happens with the person with a high diabetic or a low diabetic process. After each day, we stop the glycation, putting some drug inside, and we make a lot of different procedures just to avoid that bacteria goes inside the LDL and produce something more than the glycation that we are interested in. So this process was not made by physicists, are made by physicians and immunologists and chemists. So what we did after that, it's important to see if the glycation was efficient. So we can measure what they name the advanced glycation end products. This is the number, the concentration of this end products as a function of time in presence of the JD. We started here, so the sample at day 0. And after that, you see that the control decreased a little bit here, the concentration of the GAD. And after that, you see the increase on the concentration of this end products, indicating that we have certainly modifying the LDL particles due to the glycation process. Well, the linear absorption is important just to see in which wavelength we will turn our laser, because we can fix the wavelength of the laser just to put this in a place where it will be absorbed by the sample. So this is essentially distinction that you measure in the UV spectrophotometer. As you have particles inside, you have Rayleigh scattering. So if you remove the Rayleigh scattering, you have the real absorption of the sample as a function of the wavelength here. We will fix in 532, which is the laser, the green laser there. And you see that the LDL, which is the normal LDL, not modified by glycation, has this very interesting peak here. And after 2 days, you see that the peak practically disappears. So what you have here is essentially the Rayleigh scattering, okay? You don't have absorption. So the absorption decreased a lot. Because of this, you don't have the formation of the thermal lens. So it's the native LDL and LDL modified as a function of time. So as you see here, this is the native LDL, okay, with very big peak to valley distance. This is the control. What happens with the control? It was left to modify as a function of time, but not with glycation. Just as a function of time, you leave the sample there, it will oxidize as a function of time. So you see that the peak to valley, the theta decrease, but here in green, in a rat, pardon, you have the glycation after 6 days. So you see that the peak to valley distance with respect to the normal LDL decreases a lot. You can see here the parameter theta for the LDL, which is in time 0. We started with this LDL. This is the control, and the glycation very small here. So you see that our technique is able to differentiate the LDL, which was left to be oxidized as a function of time, not in the body, clearly, but in vitro. But the glycation product produces a very small peak to valley, indicating that this modification is very important. And this means that this LDL in diabetic patients will not be recognized, all of them, by the immunological system, and people with diabetes will have plaques in the arteries, in the different parts of the arteries in the body. So, big theta, better LDL. Small theta, worse LDL particles. Well, in terms of structure, we did not see too much different. We used a small angle X-ray scattering. You have a small angle, the X-ray here. This is the wavelength we use it. You have the scattering there. You have basically, you can do that in our lab, or we can do that in the synchrotron. But the modification of the LDL was not observed, so no detectable modification of the LDL in nanoscale. So it's a very small modification in terms of structure of the particle. However, our hypothesis is that the glycation process may consume the carotenoids, which are essentially the most important absorbers of light in the wavelength we use it, the green light, use it in the Zscan experiment. And when you remove this carotenoid from the LDL, you increase the possibility of oxidation, because the carotenoids are essentially the first line of defense of LDL against modification, against oxidation. So the glycation consumes this carotenoid even without modifying the shape of the LDL, as I showed you before with iron and copper, but it removes, it consumes the carotenoid, which protects the LDL from free radicals that we have also, or we have always in our blood. So because of this, you don't have the absorption of the green light, which comes from the Zscan. Because of this, you have a smaller peak to valley. Because of this, you have more oxidized LDL, non-recognized formation of plaques. So the first take-home message of this study is that the Zscan, okay, is a sensitive technique to identify the native and modified states of LDL. The glycation modifies the LDL particles in a way that they become more heterogenic. If they are more heterogenic, more oxidized, they have more probability to be not recognized by the immunological system and will be used to the formation of the plaque in the arteries. So this is done, is our hypothesis, that is due to the consumptions of antioxidants that all the LDL particles they have in their constitution. This was published in 2018. If you're interested, you have the reference here. But in vitro experiments, usually you can say, well, is this what is really happening in vivo? So let us do an experiment in vivo now. And I will discuss with you now illness that we have in our gums, which is named periodontitis, which is basically due to this bacteria, Porphyromonas gingivalis. You know, as a physicist, I had to learn a lot of terms from medicine, from immunology. I never heard about this bacteria, but it is the bacteria which is present when you have this periodontite in your gums. Well, the effect of this periodontite, of this bacteria, is the following. This is someone with periodontite, which is present essentially in this part of the gum, okay? Well, if you have this in your gum, this enters in your blood system. A systemic immunological response will produce modifications of the LDL. So our body, our immunological system will fight against this bacteria. And during this fight, it produces a lot of free radicals in the blood. And free radicals in the blood will attack mainly the LDL particles. So we will have more particles modified. They are heterogenic, so they will form the plaques in the different arteries of the body. Well, we discussed it with dentists, odontologists, and we will treat now the periodontitis of this guy, make the treatment, so you will have less modified LDL, reduction of the inflammatory response in the body, so healthy gums. So what I will show you now is what happens with the LDL particles of someone which started in this condition and after stays with this condition. What happens if we take the blood from this guy in the beginning of the treatment, when he arrived at the office of the dentist, and after 1 year of treatment. So the idea is the same. We take a number of patients. Here enters the mathematicians, which gives us the minimal numbers of patients that you need to have a good conclusion of your study. These are the parameters: age, number of teeth, gender, systolic pressure, diastolic pressure. So this is something that we try to characterize each group of patients with diabetic mellitus type 2 and periodontite. And we compare to some group, diabetic people also, but with gingivitis only. So gingivitis is a pre-periodontite. So you start with the gingivite, and after, if you don't treat, you go to periodontite. So we take these two groups of guys, and we will analyze the LDL particles using the Zscan technique for these two groups at t equal to 0 when they arrive at the office. Oops, someone is entering in our Anup, someone is entering in our talk.
The audience, please do not discuss anything.
Yeah, okay.
Participants.
This is not me. This is someone which is entering. Is a hacker. Is a hacker.
Yeah. No, I know you. I request to the participant, please do not sketch anything on the screen.
Yeah, it's not me. It's not me. Well, so unfortunately, it's not easy to see here, but this is the LDL particles from people arriving at the dentist office, okay? You don't have the peak to valley distance, okay? Even after 3 months, you don't have this. So peak to valley is almost 0 here. After 1 year, you have the peak to valley formed. So you see that improvement of the quality of the LDL as a function of the treatment performed by these guys. So it's difficult to see here, but the theta parameter, this is the statistic. We have to make a statistic to be sure that the difference is statistically consistent. And what statistics people measure is essentially the p-value of the distribution. And the p-value of the distribution for the theta, for example, in this line here, you see that is significant, so it's smaller than 0.05. Also the thermal conductivity, remember the DTH that we discussed in the beginning of the talk. So we are able to measure this also. So it's a significant difference between before and after the treatment. And also the linear absorption, indicating that your particles now, when you treat the periodontite, you have more antioxidants present in your LDL particles. The same thing for gingivite. So if you treat gingivite also, you have the modification of the peak to valley. You start with a small peak to valley, you increase the peak to valley. Oh, perfect now. You increase the peak to valley, so you see the p-value here is much smaller than 0.05, which means that your statistical significance is relevant. So what you can have now, for example, the measurements of theta, as I told you, the typical Zscan for the patient with periodontite after 6 months and after 12 months. So the theta here in the periodontite increase. Oops, sorry. Come back. In periodontite, you have here the increase of the peak to valley as a function of time, and you have the increase of theta in the gingivite. But see that there is a big difference between the periodontite after 1 year treatment and the gingivite after 1 year treatment. And you have a very interesting conclusion that people didn't know before, which is very, very interesting. I told you in a while. So here is the linear absorption as a function also of the time 0, 6 months, 12 months, periodontite and gingivite here. You see that even after 1 year, people with periodontite completely treated with a very nice month did not reach the level of someone treated with gingivite. Well, so what's the take-home message to finish our discussion today here? So the periodontal treatment we just saw was able to improve some periodontal parameters in diabetic patients. After the treatment, this is the very important point. After treatment, the quality of the LDL in patient group of periodontite did not reach the quality of the gingivite group. This means that the periodontite leaves a sequel in the guy, even after the complete treatment. The dentist say to the guy, okay, you are cured, you don't have more periodontite, you are perfect, you can go home. But what we saw is that even at that time, 1 year after treatment, there are some sequels, there are some memory of the blood with respect to this fight of the immunological system against the bacteria. And this still modify the LDL particles of the people. So it's very important to take care of this point, because when you are cured of the periodontite, you are not cured in the level of the blood. You have to treat the blood to remove all what remained from the fight of the immunological system against this bacteria. So the peak to valley distance, the thermal conductivity, and the linear absorption were also shown to be very adequate to determine the quality of this LDL of patients and evaluate the cardiovascular disease risk, essentially measure the amount of carotenoids present in the LDL particles. Well, this results was just published in the end of 2019 in scientific reports. If you're interested, please see this for more details. And I am obviously ready to ask your questions and to give more details about our experiments and our conclusions. And I think this is what I had to tell you. I hope this is correctly saying. Thank you very much.
Wow, Professor. Wow. Dhanyavad.
Is it okay, this?
So this is Dhanyavad means thank you.
Okay, very good.
It's Hindi forms, Dhanyavad, and it means thank you. And I'm very surprised being a physicist. The work here presented by you is fantastic. It's not very easy to carry out such type of work for physicists. Means, with the quality of the LDL, we can cure any of disease like gingivitis, you say. Uh, it's very fantastic, I think, lecture, and many of our participants are getting benefited. If anybody is having a question from Professor Neto, please type or I will mute. Unmute. Is there any question? Is there any question for participant? I think so, Professor. I have a question actually. Professor Neto, can you hear me? Hello, Professor Neto. Hello. Hello, Professor Neto. Can you hear me?
Yes, I am listening. Yeah.
So from this Zscan technique, we can estimate the good. Wait a minute. Wait.
Cannot understand. Hello?
Yes, sir. Yes, sir.
I did not listen your question.
Uh, so this technique can also be applied for other disease also. Means we can cure the other disease with the idea.
Yes, yes. The Zscan technique is very broad application. As I told you today, using depending on the time scale of the laser beam you are using, you can prove different types of process: thermal, electronics, Xray effect, etc. This can be used in all types of sample which is transparent to light, because this is the Zscan in transmittance geometry. But you can have also the Zscan in reflection geometry. So even for samples which are not transparent to light, so did not leave light pass through it, for example, a rock, you cannot pass light through a rock, a thin film of rock, it's impossible. But you have the reflection light. So you can use also the scattering, the Zscan by scattering, okay? Reflection Zscan. So you can use for all the condensed matter physics. It doesn't matter if you have gas, solid, liquids, it doesn't matter. It depends only if you use transmittance Zscan or reflection Zscan. Okay.
Thank you, Professor. It was really nice talk, and I am really thankful to you for giving our time from your busy schedule. And once you also given me a chance in your lab, and I could join. And today I could see you and feel you.
Yeah.
Thanks a lot. And tomorrow we will meet again. And so I will stop the today session right now. Thank you. Tomorrow we will see. Same time.
Okay. Thank you very much. Bye-bye.
The meeting ends.